Welcome, everyone, to today's talk on the architecture and business value of event-driven systems. My name is Corey Knowles. I'm a managing editor with Technology Advice covering IT, and I'll be your moderator today. We're thrilled to be joined by Sean Chittenden. Sean is a field engineer at Cockroach Labs and a highly accomplished expert in distributed data systems. He was formerly an architect at DoorDash, HashiCorp, and Joyent. In this talk, Sean's going to dive into the architecture of event-driven systems and highlight the business value of transitioning your transactional workloads to real-time operations. Please join me in welcoming Sean Chittenden.
Good morning. Welcome, everyone. All right, so we're going to get through a couple things as we get through stuff. We're going to go through and talk about kind of what is event-driven architecture, why it matters, and the impact on your business, and the various different ways in which this is going to impact your business in terms of engineering effort, infrastructure, and kind of looking ahead in terms of what's on the landscape and that you can kind of look forward to as organizations modernize. So. What is event-driven architecture? In our business world, the way that we talk about pushing data through the system, you will have a system of record database like an Oracle or a Postgres or something to that effect. And we talk about ETL loads and batch processing and how do we get to the close of a something, right? These are all very legacy kind of like batch oriented mindsets, and some of them have real need and the ability to like batch out and close out for fiscal reasons. But the whole idea of doing something in batches is kind of a legacy concept for a lot of workloads. And frankly, there's just not a lot of appetite for that from customers. How do you go in and do things in real time so that you place an order and you get a notification? Like we've moved to this very much instantaneous gratification kind of world where you buy a thing, you go do a thing, and you expect something to happen in real time. And in order to go do that at this point in time, there is a lot of changes that have happened to our infrastructure and architecture to support that. So we need to talk about events, producers, consumers, and we'll briefly touch on those. But then we'll talk about some of the accidental complexity that have come from just the state of technology over the last 20 years and where we are now means that we can go back and revisit some of this stuff, which we just have never had the opportunity to do in the past. So we spent basically the last 20 plus years, depending on your, history, you may have seen this as 3-tier architectures. If you're, familiar with data centers, we're now in kind of the cloud universe where you have, users, CDN, load balancers, app servers, and databases. You can kind of bucket this into a couple of different, tiers right. So you've got routing, you've got compute, and you've got your storage and database layer. And what's interesting about this is we spent the first, last 20 years effectively figuring out how to load balance stateless applications. And we're really moving into this area where it's like, hey, why isn't your data, load balanced as well? And when you get to the point where all of a sudden you're now load balancing your data, this really opens up the possibility of having your database do more. The reason that we had these centralized databases and then we started taking functionality out of the database was because databases used to be a single point of failure, but that's not the case with distributed systems and distributed SQL in particular. So, if you look at what this looks like now as possibilities, we can go back and reimagine our architecture so that you have a CDN, talks to an app layer that goes and generates some SQL, that goes and makes a write or some kind of a DML operation, data modification of a record. And then out of the database, if you go and produce an event, you're able to get high fidelity, events without having to go back and change your application. And that's really kind of the crux of what we're going to talk about here in today. So what's an event and how do we talk about this, right? So if you've got kind of like the primary purpose of an application server, effectively what they're doing is they're receiving typically some type of a message from a client. And what that the app server does is it converts an object state, does a load operation, and then it goes and converts that into some type of an intent, and we send that intent off to the database in the form of, like, let's say, an update. In this particular example, we're talking about, changing an email address. It's contrived, but whatever. But the intent is, I want to go and change my email address. That's what the user communicated, or the client communicated to your app server. And it's funny how that, in the middle there, we do that load operation, and then we get to, like, the SQL representation of this, and what that is actually back to what the user originally communicated, which was update my email address. And so we go through this kind of, like, dance of marshaling an object, and then doing the basically the diff operation on that object, and then we go and convert that back to SQL, and we go and send off that update. But the important thing is there's that intent there, which is an update. So let's see. So you get that update, and then what happens with that update, right? There's different types of updates and events that can come from this. So you have a SQL update, which is it's a notification of an event. Effectively, it's coming into the database. If you squint and look at it, and the ways that we talk about this is do X on record, right? A Y effectively is what that looks like. And so you do that update, and you'll see the transport for these types of messages in the form of SQL posts, some kind of REST operation or a gRPC, which is and then coming out of that, we'll see log messages where it's like, hey, user Y changed, or we have some type of change data capture event that gets emitted, CDC message that comes out. And you can see that, like, coming into the system, you've got synchronous events, right? So you've got SQL, REST, RPC. Those are all typically synchronous operations. And then you have asynchronous operations that come out of the back of that as a result, a consequence, right? And so, there's an important element to these messages. You've got just event notifications, like with what the user intent, which was like update or change your email. And then you've got kind of like this very naive 1.0 type of approach, which is like the user X changed their email address, or user X signed up, something to that effect. It's very simple, but it does provide some amount of real-time notification that, like, something happened in the ecosystem, your application ecosystem. Well, when you have that type of simple event notification system, that actually has an important downstream consequence on the database, or like your application. Because if you think that doing just an event like this is going to be sufficient, you're probably wrong, unfortunately. Because if you go back to that JSON that we were looking at a minute ago here, that we were looking at here, there's a whole lot of additional information. And that additional information, if you did user X or user 456 change their email address, but maybe you need to go and talk to it and send off a notification to their phone or something like that. Well, how do you get that information? Well, you can't if you just have an event that says user X changed their email address. What you have to do then is you have to move from this very basic 1.0 universe to a 2.0 universe. I'm calling it that, where you have event carried state. And this is important because if you don't carry the state, when you go and send off that notification, you're going to have to go look up that same record anyway. So, thinking about this naively, if you go do this 1.0 event-driven, approach, you're going to send off a note, RabbitMQ, Kafka, whatever your jam is, right? You're going to send off this notification, and then that other consumer is going to go pick up that change, and then they're immediately going to go back to the database, the system of record for the user, and they're going to go and make a query. And if we've spent all this time figuring out how to decompose our applications into microservices, we did that for scale, we did that for organizational boundary purposes. We've done it for a bunch of reasons. But the net result of that is, all of a sudden, we're going to go back and cause this scaling problem for our database, right? And we can elide that problem by simply carrying additional information with that. So if you have this additional context that goes with the message, it sounds simple, but it's really important. If you have this additional context, you're able to elide that lookup back to the database, and it means that events are now pretty scalable. Obviously, sometimes you have to go back and query, but this fundamentally unlocks additional behaviors inside of and structures inside of your application or infrastructure. And if you go look at this, right, like there's kind of a couple of different things, right? So if you've got these messages, right, object, was verb, like, user object changed, changed it to, was, is, now. You're going to figure out that there's a couple of different ways that these messages get injected into your ecosystem. You've got a single producer, single consumer, right? And that's, pretty simple. We're going to talk about the math of that in here in just a second. You're going to have multiple consumer, single consumer. You don't see that too often in practice. Maybe you're ingesting a lot of events and you need to get like, small amounts of notifications. Again, it's not very common. Multi-producer, multi-consumer, been there, done that, got the t-shirt. That's a really like kind of ugly infrastructure to have to operate and exist in, because you've got lots of different lots of different producers producing messages of different types, lots of different consumers looking for different things. So the contract that you have to establish between your producers and your consumers is really difficult. And really kind of the sweet spot is this single producer, multi-consumer kind of universe that you kind of want to aspire to live in. And that was always really hard to do with a pure microservices infrastructure. By that, I mean, if you had a bunch of different teams, right? Like, you've got like 100 different microservices kicking around inside of your organization, and they're all collectively producing things. And the reason they're all producing things is because there's scale that comes from that, scale advantages that come from that. Well, that means that you have to go and coordinate a change across hundreds of different microservices. And that's really difficult potentially to go do. It depends on the engineering discipline. But if your organization's moving fast and shipping quickly, that quickly poses a problem. And it's going to take like 3-6 months to go and refine the type of message and get it like good alignment across all of the producers and the consumers. So if you can get to a single producer, multi-consumer, that's at the moment, at least as near as I'm aware, that is as close to ideal as you're going to get. And so we want to talk about like, how can we get to that idealized state sooner rather than later? So, let's talk about kind of the expense and complexity of living in these different quadrants and the complexity of that, so that, hopefully some of the language of this, you can internalize and take back to the organization and kind of internalize. So in the, what we're going to use this kind of like, high level, big O, notation, it's going to be, how much is it going to cost? And, cost is kind of, it's relative, but you can start to figure out what the order of magnitude approximations are for all this. So if you've got, the single producer, single consumer, you're basically just transporting a message from A to A, right? Like, this is not very hard. Maybe you're the producer, maybe you're the producer and you're also the consumer. So single producer, single consumer, super easy, right? So you've got maybe like, hypothetically, you've got 2 producer call sites that you have to go and decorate to emit messages. You've got, 1 unit of person time. You got 2 teams or something like that. It's reasonably cost, and like, the reference unit, whatever your reference widget, like there's just some kind of like base cost, we're trying to just approximate something like this. Unit cost of 4 for single producer, single consumer. It's really, really cost effective, really cheap, but like not particularly useful because, you're trying to send a message across the entire organization to do something that meaningful to everyone. If you do the multi-producer, single consumer, all of a sudden you see things like in the math, like there's a couple of different variants here, like depending on the size of your organization, you start to watch the complexity of this get really high. So if you've got, 40 different teams, you see that like, this unit cost of 105, like it starts to get expensive pretty quick to be in this multi-producer, single consumer kind of universe. And if you get to like the real pathological case where you have multi-producer, multi-consumer, you realize that where possible, you really want to move away from this, right? So, because the more teams you have, the more expensive this gets. And like having worked in organizations with much higher, many more than 40 teams, like 100 teams, 300 teams, the cost is exponential, especially when you have a tightly coupled business where you've got lots of different teams chewing on the same customer golden workflow. So we really want to back away from that where we can, and instead get to this like, kind of much more scalable, idealized state, which is single producer, multi-consumer. And as you can see, like, reference cost of 300, 300 reference widgets, units, whatever, getting down to like 60. This is this is great, right? Like this means that you can add additional teams and you kind of have this like fixed overhead, but like you don't have this exponential growth. And so if you take an architectural decision and then you back that into the organizational cost, there's real implications to the way that you go and approach this type of problem of providing an event-driven architecture. Because if you want to go and ask all of the different people in an organization to go do this, there's a pretty high cost. It's the TLDR of what I'm pitching here, or like I try to explain. So if you have this kind of like bespoke mindset where every team is responsible for both looking to the database and then also producing an event, not only can you just visually look at this and say, that's kind of ugly, like organizationally, that should match the organizational math I just posted a second ago, which says, hey, you have to go and do double work and you have to coordinate all this stuff across all these different teams because everybody is producing into that event bus, right? And the type of message, the structure of that message changes for every single application, every single team. You have to coordinate that. You have to talk across the teams, Conway's Law. And then you also have to go and synchronize that for releases and which is like kind of like a real life meat space version of Amdahl's Law. And it's just, it been there, done that. You really, if you can, avoid it, right? So, pseudocode, this is Go, right? I'm not saying that all applications, all teams are broken everywhere, but if you use this kind of like mental framework where there's going to be some object and you're going to like call some save-ish kind of an operation, it's going to go and emit an event, and then you're going to go do maybe some cache operation, and you're going to just save it to the database, you're going to end up in a sad place because that type of a bug is way more complicated code paths than this. This is, super distilled down just to kind of like make the point. There's going to be a bug and there's going to be a rate, maybe 1% of the time, 0.5% of the time. There's the possibility, the amount of entropy that happens because the business is moving fast and there's lots of code in flight, and like it's a non-zero probability. But if you can simplify things, right? If you can have the events produced by your system of record, all of a sudden you end up in this really neat place because your application is no longer required to go and have those event emit operations. Instead, the database does it. And not only if you can get the system of database or system of record to go do that, you're in a situation where the consistency, 100% of all updates are going to receive this exact same treatment. The structure of the message, well defined. You don't have to worry about that either. So there's no kind of like half-baked things that you have to go and chase down. And that has big organizational implications, right? So we're going to talk about kind of like, the next part, which is like, if you've got producers and consumers, which one of these would you rather see or have your business, your organization do? Would you rather have something where you have consistent messaging like you have on your left, or would you rather have something where you're conditionally, handling everything all over the place in your producers, in many different producers, right? And I would argue that what you want something that's consistent and stable, so that you on the left side of things will always have like stable inputs, right? You've got a well-defined contract. And so it's easier to filter on the consumer client side of things than it is on the producer side of things, right? If you can see, in producer, if it's a test, don't emit it. Like that's potentially really difficult because then it makes it hard to test things all the way. Instead, emit a consistent message everywhere. And then on the consumer side of things, align the actual action that has real world implications. So, if you can, bias towards filtering in the client. And so if you now are producing a consistent message everywhere out of the system of record, makes it really easy. And then your consumers, you can go in and take your consumers and you can bucket them into like a handful of kind of like pretty easy to understand patterns. So you can have things that could consume these event streams. You can have copiers, right, which just takes a message and receives it from one queue and then drops it onto another queue. Really easy. Now you've got the message in two places, and you can do that for basically, like, I don't call it poor man's replication, but like a way of replicating data. You can, do the next, one, which is I'm going to take a message and I'm going to go and transform it somehow, and I'm going to plop it onto a different queue because we've got some kind of a transform. But if what you're doing now is reading an input, filtering it, and doing something, or transforming it, and then dropping it, or filtering the next type of operation, where you're saying, hey, I'm going to take this fire hose of events that's going to come off of the QA, and I'm going to read it and see if I actually care about this, right? Is there appropriate selectivity? And if there is, then I'm going to go and take it and I'm going to drop it into QB, right? And then filter it. And then, or maybe I'm going to say, like, you know what? It's on QB, and I know that it's already been filtered. I know that the inputs have already been transformed. Because of that, I know that I'm actually going to go and take action. I'm going to go and send an SNS notification and go and notify the actual user. I'm going to send an email. I'm going to go and notify a vendor, whatever it is, right? Then that makes a pretty simple component for engineering leaders who are looking at a large business problem to help that, or architects to go and decompose the problem. And if you're an engineer in this ecosystem, you're like, hey, I can go and do read from A, process, whatever process means, and drop onto event B or QB. And that's pretty nice. So how do we get there, right? If we go back and we look at this, we really do want to be in this kind of single producer kind of mindset, because it means that at this point in time, I'm not talking about how do my contract at the top of the funnel, request funnel, and coordination. What instead I'm talking about is how I consumed this message and how I did some work with it. And that means that you're focusing much closer to what your customers care about, which is whatever the business value is that you're providing to the world. So garbage in, garbage out, garbage in, guaranteed out. How do we get to this high level of fidelity with regards to the types of messages that are produced? And that's really where use of Cockroach as a system of record comes to play, because it's a distributed database. Because it's distributed, you don't have to worry about scale in the same way that you used to. If you had a single server, single point of failure kind of database, traditional database, you would never consider this, because it's just like you would never use triggers in a database. The reason you don't use triggers in a database is because of scale, and we've as an industry basically throwing that out there so that it becomes it becomes gospel. You just don't use triggers if you're in a scale environment, because you're going to run out of resource, because you're putting work into a single point of failure. Well, in a distributed system, that's not the case, right? So Cockroach is distributed SQL, so you can scale out, you can push this kind of complexity and delegate it to something that can get you that 100% consistent treatment. It's easy to use. It's Postgres wire compatible. It is transactional, and it becomes your, the enabler of this kind of nirvana state, which is it's your single producer of events. So what this looks like is you have a load balancer, you talk to Cockroach, and Cockroach, just in a nutshell, when you issue a query to Cockroach, Cockroach is collection of in AWS EC2 nodes, VMs, bare metal servers, however you decide to deploy it. But you have client goes through load balancer, talks to a node. The data is distributed across different ranges. So kind of for this talk, we're not going to get too into detail, but what's important is your query will route to the appropriate node to go make the execute the query that you sent in. And we'll do this for millions of ranges and 100,000 nodes, whatever it is that you need to do. So if you've got that kind of an architecture, what does that mean for events? It means that as you add nodes, as you add data, because this is all a single unified distributed system with consistency across all the nodes in terms of the software, your application can speak SQL, talks to a database, and that database now emits the same event into your event bus, which means that all of your consumers know exactly what they're going to get. And you don't have to worry about in your application having your applications emit different types of events or messages. Instead, you can have all your consumers consuming the exact same type of message. Very convenient. Being able to declaratively specify what tables, because everybody's familiar with tables and system and records, is you can declaratively specify the changes and change feeds that you want so that your applications can consume these records in a stable, consistent manner. And what does it look like? It's really easy to process, but there was no application code required in order to make this all happen. So change feed, you have a before and an after record, and you can see, right, in the before record, I had no vehicle ID, and this is just some made up example here. But like this is, we took a SQL row, we pivoted it, and emit it as a JSON event. And this JSON event, before record, what the old value was, after record, that's the new value. If it's a insert, there's no before, and in a delete, there's no after. And as a consumer, you can quickly reason about what's going on. You can figure out, because you've got event carried state, like I was talking about earlier, you don't have to go back and look to the database to go in and figure out, hey, what was the change? What was the value here? You can go and archive this, and you can use this for auditing purposes. There's a lot of utility that comes from this stuff. So automatic, event carried state means that your business can just process data and not worry about the scale. Prior life, when I was working at DoorDash, we had an interesting situation where we needed to manage inventory. Everybody needs to manage inventory, but we also need to manage inventory in real time. And as purchases and orders were flowing through the system, we would actually emit events, and then we would process those events, and we go and take action based off of inventory to go do whatever it is that we needed to go do. And there interesting case studies publicly available about what this looks like and the efficiencies that get from this, because now instead of having to worry about all of the mechanics and plumbing associated with getting this real-time architecture in place and coordinating all this, instead there's a very discrete pattern that you can use in order to have a microservice make a SQL update, and all of a sudden you've got real-time events that are able to flow out of this particular architecture, and it's fast. From a development perspective, it means that your business is focusing on customer value as opposed to dealing with the toil of plumbing and kind of the bits of pushing things around internally. So Cockroach, as a system of record, single event producer, it's Postgres, it scales. It allows developers to focus on just SQL and just the business problem, the data that they have at hand, and not have to go back and revisit all of these architectural problems. Instead, you can go and take an existing application that doesn't have any event-driven concepts in its architecture, and you can add Postgres to the mix, add Cockroach to the mix, and shoehorn it in because it speaks Postgres, and begin to move to an event-driven architecture without really fundamentally having to go back and revisit your entire infrastructure architecture. And with that, Corey.
Well, Sean, thanks so much for the presentation. Let's hop right into Q&A here. If anyone has any questions, feel free to type them into the chat box, and we'll get Sean to answer. First, we have a question here. Can you elaborate on how Cockroach DB eliminates the need for tools like Debezium and how this impacts the day-to-day operations of a database administrator or engineer?
Yeah, it's batteries included. It's a good question. Like it's batteries included, single binary deployment. There's no sidecars, there's no polling. This is all done at real time. I've actually integrated this into soft real-time factory floor type applications, which I never thought I would, those words would ever come out of my mouth, but like the ability to go and do this and see events emitted, within milliseconds, low milliseconds, with low millisecond delay for committed transactions, and then being able to feed that along to, downstream systems. That's very much a doable thing. And it really is just like, it's batteries included. You don't have to go stand up an additional service. You don't have to worry about, some external schema management for this. It's kind of all just right there.
Nice. We have a question here from John Norcott. Doesn't this require moving business logic outside of application code and into the database?
Not logic. This is basically forwarding. So when you just like what's on the screen here, when you do this create change feed, you could potentially filter, and you could push some filters into the database where you put a query on these create change feed statements, like create change feed where. But it's not like you're doing complicated programming. Instead, you're just saying, like, when there's a change to table A, emit event to sync B, Kafka S3, whatever it is, or some HTTP webhook, whatever it is. There's definitely, I think, room for debate as to whether or not you want to have triggers or not in the database. I think that there's times where that's very much needed, and you can now approach that problem without running from it because of the scale issues. But certainly from a coupling perspective, like, there's times where it makes sense and times where it's not necessary. But in this particular case, there's not really logic here that's being put in. Instead, you're making this policy level infrastructure decision that says, whenever I have this particular a change in the data or record for this particular data set, whenever there's a change, I want to emit that change, and that's kind of handled by DBAs or whoever handles the operation of the database. But it's kind of an infrastructure policy level thing, as opposed to being logic that's handled in application. The decision to get data from A to B is that's your data infrastructure, and not really part of your application infrastructure.
All right, we've got another one here. You mentioned that only committed transactions are emitted from Cockroach DB.
Yeah.
How does this enhance the reliability of the data and events received by consumers compared to other systems?
You don't have to deal with error handling in the same way. So if you have some type of transaction, you as a application owner, you can do begin, insert, commit, delete, rollback, and no message gets deleted. Imagine if you were trying to do a multi-stage transaction with events. If you're going through a typical imperative programming language and you've got A, B, C, whatever it is, whatever the sequence of steps is there, and along the way you emit something and you don't gather that all up, or maybe you're using libraries where the event emission, like the decision to emit an event has been delegated to a client library. Like, let's say I'm doing something where I'm making up a scenario here where you have a user library that you import, and that user library happens to say, hey, if you change my email address on this object, I'm going to go and emit an event. Mm-hmm. Great. The problem with that is you didn't know that was happening as a side effect. But if you roll that user update back, let's say, there's no way of putting the genie back in the bottle. You already emitted this event. You have to go and retract that event. With something like this, you commit your transaction, and then the change feed events get emitted. It's very simple, very clean. It's not an application concern. Instead, it's something that gets pushed off and delegated.
Okay. Next question's coming from Sierra Staggs. Can Cockroach DB be used with Confluent or Kafka as the queue in a stream processing use case?
Yep. It's one of the most popular syncs that we use. So we have a change feed, and then it emits to a sync. Different types of sync, Kafka, S3, whatever. Kafka is certainly an option there.
Okay. Next question is, so data in the change feed is the complete database record?
It is, yes. It is done on a messages that are emitted are row-based, so the entire record is emitted. You have to, when you specify the create change feed, include the diff option if you want the before and after. Otherwise, it will only emit the result.
Okay. Let's see. Next here, we have another question. As businesses grow and data inflow increases, how does Cockroach DB's event-driven architecture scale to accommodate these changes without compromising on performance or reliability?
As you add nodes, in the Cockroach architecture, you add nodes, you get scale. So if you have 1 million transactions a second coming into Cockroach, great. You've got enough horsepower to handle that SQL. You've also got all of the clients, the Kafka clients that are doing the production, let's say, integrated into Cockroach. So Cockroach will emit, the similar number of events out the back end. I think the largest, backfill Kafka job. Actually, we tipped over a Kafka cluster because it was doing more than 10 million messages a second,
Oh,
and that was just what was necessary. And Cockroach happily stood up and just fire hose that through. So um, frequently Cockroach can drive more events than downstream systems can typically consume.
oh wow. We have another one here from, and forgive me if I pronounce this wrong, Radu Papa.
Mm-hmm.
Can Cockroach DB participate in distributed transactions with other systems using, say, different technologies?
It Not directly. Cockroach is acts as a single source of record. It's a system of record. It acts as your source of truth for a piece of information. If you wanted to do tightly coupling with an external system, the application would have to do that. If you wanted to have loose coupling through like an HTTP sync, let's say, where you had the top of the request funnel was being written to Cockroach, and then you wanted to have some downstream like tight coupling there, you can kind of do something with a change feed, because change feed messages, when you receive a webhook, it's not until you post a response back 200 OK that Cockroach advances its internal cursor. So you can create some kind of tight-ish coupling there between Cockroach and some downstream system that goes and relays the information. But Cockroach itself doesn't do like two-phase commit to go and synchronize with some external provider, in the middle of the transaction stream. Instead, this is very much about post-committed records. So it's important for us to have, for our customers, we think, to have kind of a simple model there in terms of how to consume this, so that some of the really icky Byzantine situations that can exist don't exist.
Thank you. I have another question here regarding integration and implementation. It's tied to the change feed situation again. What are the key considerations for businesses when integrating Cockroach DB's change feed with existing data pipelines, especially when transferring to platforms like S3, webhooks, Kafka?
The initial backfill. Be mindful of the initial backfill. It's not typically concerned getting some of this stuff stood up, but like where we'll see kind of like, I'll call it rough edges, from an experience perspective, is that initial backfill. A lot of times they're Cockroach, you will just, let's say I've got a workload net right now that I'm working with. It's got 100 billion records, and you want to go turn on change feeds on that. And that's fine. That'll totally work. But the thing downstream needs to be able to consume 100 billion records, because when you go and do that with an initial backfill, you're going to go drop 100 billion records onto like whatever your queue is, S3 or whatever, and like there's consequence to that, and there's a cost to that, and so you have to be mindful of. The other one that you typically see is schema management. If you turn on change feeds and you go and make a lot of changes to your schema in rapid succession, your clients downstream have to be aware of some of that stuff, and that's normally much easier to consume to coordinate. But if you've got some downstream JSON serialization library, Parquet, whatever it is that you're using, and it is expecting a field that doesn't happen, like, you just got to be careful that you're not going to blow up all of your consumers because you maybe do an alter table delete column. I don't think you should do that in practice, but maybe that's a thing, and you have to be a little bit defensive in your programming.
That makes sense. Makes a lot of sense. I've got one more here. Beyond the immediate benefits, how can adopting an event-driven architecture with Cockroach DB position businesses for future technological shifts and advancements in the database and analytics space?
If you've got this kind of point of indirection between your data and your event production, as you evolve, a limited number of people have to be involved in modifying this, instead of having to coordinate across the entire organization, from your application team, your database team, storage team, whatever. So your app team, database team, and then your analytics pipeline further down. You've now reduced the complexity there by at least a third, right? You don't have to deal with the application team making changes there. So that at layer of indirection, and reducing the scope of the involved parties means that data plumbing, your data plumbing portion of your business is really limited to your storage team and your analytics team. And there's just fewer people involved. And if you've got fewer people involved, your business is able to move faster. Your business is moving faster. You're paying attention to customers more. So, I think the benefits are going to show up typically indirectly, but they're going to mean that you're able to execute faster. It's the same reason typically that businesses that adopted the cloud have outcompeted businesses that have stayed on traditional metal, just because they can just iterate faster. And so businesses that iterate faster typically win.
Makes a lot of sense. Well, Sean, it looks like we've been through all of our questions here. How can people learn more about Cockroach DB and event-driven architecture?
Yeah, so we've got two kind of like decent resources. One of them is if you go to cockroachlabs.com, we have a university training course there, Cockroach Labs, to go and get certification. If you're interested to go and kind of learn, kick the tires, and figure some of this stuff out. There's also a bunch of great resources there about change feed management. I think that maybe the slides are going to be available for presenters. We actually have to circle back on that. Maybe I actually just don't know. Certainly Cockroach Labs University is a very good resource to go and look at in order to go and get started with some of this stuff.
Cool. Well, thanks so much for joining us today, Sean. Your insights into the transition from batch operations to real-time processing, giving us a lot to think about. And we also want to thank everyone who's come to join us today. We appreciate you. We appreciate your questions, and we hope that you found this session to be valuable and informative. Before we conclude, I'd like to remind everyone a recording of this will be available shortly as well. If you have any further questions, please reach out and let us know. Once again, thanks, Sean, Technology Advice, Cockroach DB, and everyone. Hope you all have a great day.
Thank you.